Sunday was what, 41 to 62? We'll start with some questions. You can, questions from those ones, or previous is okay too, I suppose. Anybody got some cues that need some answers? Blake?
Can you do number 62?
Yeah, dog. So 62, we're asked to convert this into a polar coordinate. So 4 over and 9 up is like here, right? Agreed? So the angle I'm looking for is this one. So I know that r squared is going to be x squared plus y squared. So r is going to be 16 plus 81, which is 97. And theta is just going to be the tan inverse of y over x. Since we're in the first quadrant, I don't have to worry about anything else. And I'm done. Right, there's my r theta. So I got my r and my theta. Bingo, bongo, bungo. Is that cool? Neato. Who else did I see had a hand? Enzo? 46 part A. Okie dokie. I didn't grab that page. Silly Mr. Kulik. You know, it happens. All right. It says in question 44. Okay, sweet. Assume at the exact moment that Matt hits the ball, there's a gust of wind that acts in the same horizontal direction of the ball at a speed of 6 feet per second. Write the parametric equation for the flight of that ball. Okay, so all I'm going to do here for this, Enzo, is take the force in the x direction and just add 5 to that. So maybe we'll call this new or something. Oh, I'll put it 46. So really the our x of t just turns into like, is it 115 was this one? Yeah. So 121 cosine of whatever. What was it? 41 degrees. And then the y at t is the same. So basically that just added to the horizontal force 6. Does that? Angle does not change. What that angle is going to do is it's going to just determine the amount. Since that wind is blowing exactly horizontally, only some of that 6 miles per hour is going to get directed into the ball. Basically cosine 41 of it. You know what I mean? But it basically is just the same problem now. Just that the initial speeds from the horizontal and vertical don't match, right? The vertical is still 115. You know what I mean? Does that feel okay? You got it? Okay. Maddie. Yeah, man. So do that the exact same way we did 62. So 511 is like here. This is R, that's theta. So R squared is 5 squared plus 11 squared. So R is 25 plus 121. So that's 146. And theta, since it's in the first quadrant, is just tan inverse of y over x. And you're done. Bingo, bongo, bungo. Is that? Yeah, you'd want a number there. But I just didn't want to, you know, like, we did all but calculator. Keep in mind that, what mode? Degrees. Yeah. The directions are asking for an angle between 0 and 360 degrees, so should be in degree mode. Directions, you know. Katie! 50? Sure. It says sketch the following polar coordinates, or polar points. Okie dokie. Are we doing all of them or just some of them, or? Sure. Stick that down there. Okay. W is -5, 135. Yeah. So I would start by turning -135 into positive 225, just by adding 360. Those are coterminal angles. All right, so 30, 60, 90, 120, 150, 180, 210, 240. So like halfway in between here is like my 225. But since it's -5, it's going to be flipped and going to be on this side. And then I count, so 1, 2, 3, 4, 5. So that's W. And then you said Z was the other one we were interested in? Okay. So Z is -6, -pi/4. So again, I would start by turning -9pi/4 into a positive angle. So if I add 2 pi to that, I get -1/4 pi. If I add 2 pi again, I'll get positive 7/4. Which again is 315. Which is the way I'm going to think about it, because it's easier to tell if it's not on one of the 30-degree lines where it's supposed to be if I'm using degrees than it is fractions, you know, like where's a fourth fall between a third and a sixth, it's like, but degrees, it's easy. So 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330. So 315 is like right in there. But we're negative, so we flip to the other side. So there, we're talking that. And we just count 6 out now. So 1, 2, 3, 4, 5, 6. So Z is right over there. Does that feel good? So again, don't be afraid to convert radians to degrees if it makes life easier on these plotting ones in particular. You know, especially if the denominator isn't 3 or 6, or you know it's not going to land on one of the grid lines. Estimating where that that thing is not trivial if it's all fractions. It's like, ew, it's too hard to think about this. Let's just convert it into degrees, and then it's really easy to tell where it goes. Okay. Anybody else? Okay, cool beans, dudes. Let's pick up where we've left off. Last time we've been talking about the polar coordinate system. Today we're going to start talking about polar functions and potentially some types of polar functions. Okay, so remember from last time, we talked about how to convert between the polar coordinate system and the rectangular coordinate system, right? To go from polar to rectangular, we just do r cosine theta to get the x coordinate and r sine theta to get the y coordinate. And to go from rectangular back to polar, we use that r squared is equal to x squared plus y squared, and that tangent of theta is y over x. So we have these two tools, right? What we're going to be doing today, or at least for starting, is to convert a polar function to a rectangular function. So let's say we want to or that we have r is equal to 6 times cosecant theta. So that's a polar function. I can tell because the variables are in terms of r and theta. Does everybody see that? Okay. So to convert this into a rectangular function, I'm going to be using the same two rules that I used to convert polar coordinates into rectangular coordinates. So I'm going to try to either come up with an r sine theta, an r cosine theta, or something like that. Okay? So I noticed right away that cosecant is the same thing as 1 over sine theta. Oh no, Mr. Kulik, you telling me I have to remember these identities? Yeah, man. Yeah. Okay, everybody's good with that? If I then multiply both sides by sine theta, what do you notice that we have on the left-hand side there? I have r sine theta, which is the same thing as y. Y. You're guessing, you just guessed the wrong one, but that's okay. It was a 50-50, right? It's okay, man. I appreciate you taking a stab at it. We're taking risks. Learner profile. All right. So let's just kind of see what this picture would look like on our calculator, right? So the first thing I'm going to do is I'm going to change my mode. I'm going to switch back to radian mode and go to the polar function option. You notice there it says POL, that's short for polar. So notice that my y equals menu is now starts R's, because that's what a polar function starts with, is R equals. Then we'll do 6 divided by sine theta, because our calculator doesn't have a cosecant button. We'll just write it as 1 over sine. I'm going to check my window real quick. So my theta range goes from 0 to 2 pi. That's great. And my standard window goes from -10 to +10. That looks good for both x and y. So I'm going to go ahead and graph. And look at that. Looks like the line y equals 6 to me, doesn't it? That's neat. Okay, let's do another one. So I guess we'll call that example A.
So then what about the x value?
There isn't one.
Oh.
It's just the line y equals 6. Yeah. It's not a coordinate, it's a function here, right? It's not an xy point. It's a function, right? So y equals 6 is just the equation for a line, a horizontal line, right? We're not like an ordered pair, we're missing a coordinate. These are functions, so a function becomes another function.
Okay.
Right?
I get it.
So let's say we have r equals 6 cosine theta. Well, this one turns out, although it looks just as simple, turns out to be considerably more complicated algebraically. Let's actually start this time by looking at the picture, just to get a picture of what it is that's going on here. So I'm just going to do 6 cosine theta in my calculator. Ruh-roh, Raggy. That's a circle-ish, right? Is it a circle? It might even be an ellipse. Hard to tell from that picture. I think it's a circle, though. Let's count real quick. So it looks like we go 1, 2, 3, up. And then starting here, 1, 2, 3. Yeah, it looks like a circle to me. Silly rectangular window. It's the thing that kills me off this calculator. It's a lovely machine. Why can't we just build the square window? I don't understand. Anyways, they're being cheap or something, I think. Okay.
Can't you make the zoom a square?
Yeah, it still doesn't look that square, though.
Oh.
If you do zoom, there is a zoom square option. Yeah, but now, like, look at how lumpy that circle looks.
Yeah.
Right? Look at this lumpy looking thing.
It's not a healthy circle.
No, it doesn't look great. Yeah. All right. So let's see how we do this thing, right? What do you notice right away if we try to get like an r cosine theta? Can we manage to do that by rearranging this thing? No, man. I can't get the r and the cosine theta on the same side. Right? I can get r and 1 over cosine theta, or I could get cosine theta and 1 over r on the same side, but that's not what I need to convert it straight to an x. So what am I going to do? Well, I'm going to start by squaring both sides. Nope, I lied. Let's not do that. That's harder. Let's multiply both sides by r. That's a better idea. I want to get the r squared, but I don't want to make a cosine squared. That feels like a mess. Everybody's okay with this? So I have r squared equals 6r cosine theta. Hey! What do you notice? That's x, right? Mr. Kulik. That's pretty cool. And hey, r squared, what the heck is that? X squared plus y squared. Right on. This is looking pretty promising. Okay. So what should I do now, though? This is kind of a mess. Who remembers what the equation, when we looked at this, the graph was a circle, right? You guys remember the equation for a circle? Right? That's our equation for a circle. X minus h squared plus y minus k squared equals r squared. So what I'm going to do, I'm going to subtract that 6x over, and I'm going to have to do what? The initials are C, T, S. Completing the square. Do you guys remember how to do this? Okay. So let's just review real quick on what's going on here. So if I have something like a plus b squared, when I FOIL it out, I get this, right? What I'm going to do is I'm going to try to make that polynomial so I can use that perfect square factoring. So if I go and I look at ours, -6 is my like my 2b, since a is clearly x, right? So I need to figure out what b is. If -6 is 2b, what is 1b? -3. So I'm going to add -3 squared to both sides. Everybody's cool? This now automatically factors, since it's a perfect square. I know it's a perfect square because I just made sure it was a perfect square by adding b over 2 squared to both sides. And what do I have now? Diggly dog darn darn equation of a circle, man. What? Notice that this is a circle, right? The center would be at 3, 0. So there's really like -0 there, right? And the radius is 3, and that matches our graph. You guys agree? Cool beans, Mr. K. That's not so bad. I mean, they can get worse. Let's do another one.
Have to. It can always just get easier.
Yeah. Okay. -5 cosine theta plus 4 sine theta. Let's take a look at what that bad mama jamma looks like. I'm going to go ahead and graph this back on my standard window. Going to get rid of the square one. Oh, booger schnitzels. It looks like another circle. Well, that's okay. We've just seen how to deal with this. What's my first step going to be? Multiply both sides by r, right? That'll get me the r squared on the left-hand side, which is cool. And that gives me negative 5 r cosine theta plus 4r sine theta on the right-hand side. Remember, r squared is x squared plus y squared. R cosine theta is x, and r sine theta is y. So, hey, no worries. That's not so bad, right? No big deal. All right, let's start our completing the squareage. So I'm going to add the 5x over. I have to complete the square there for the x's. And I'll subtract the 4y over, and oh no, I have to complete the square again for the y's. Oh no! It's not that big of a deal, guys. Why are you freaking out? I don't know. I don't know, man. It's Tuesday morning. It's 9:42.
It's Monday.
It's that day then, you know. Oh, no, there's no squared on the y. But yeah, there was something wrong with that. All right. So, complete the square for the x's. What do I need to do? I need to add 5 over 2 squared to both sides, right? And what do I have to do to complete the y's? I'm going to add negative 4 over 2 squared to both sides. Also known as negative 2, but I'm going to write it in the silly way so it's super clear when you go back and look at this what it is Mr. Kulik was doing. Everybody coolio so far? This guy factors to just be x plus 5 over 2 squared. The y guys factor to just be y minus 2 squared. I reduced negative 4 over 2. And then here I'm going to have 25 over 4 plus 16 over 4. So that's going to give me 41 over 4. And that one would have been a tough one to come up with the radius of being the square root of 41 over 2 from looking at the picture, right? Diggly ding dong doog, Mr. Kulik. It's a good thing we have a way to do this algebraically. Right, where my center here is negative 5 over 2, 2. That would have been reasonable to glean from the picture. But the radius would be the square root of 41 over the square root of 4. That would have been tough to come up with without doing this algebraically. What do you think? Completing the square? It's not so bad, mostly because you'll never run into a leading coefficient other than 1 when we're doing these, and that's where the completing the square gets a little bit hairier. Alyssa.
Can you just explain how you got like the plus and 5 over 2? Like why are we dividing?
Yeah, so the reason we're dividing them by 2 is we're trying to use this perfect square factoring pattern. So when I FOIL out the perfect square, I get 2 times a times b as the middle term. So if my middle term, in this case, has to be 5x, so I know the a term is x, right? Because the x squared has to be a squared. So 5 is 2 times b. So I need to get b squared then and add that to both sides. So if 5 is 2b, then b is just 5 divided by 2. And is it always going to be divided by 2? As long as the leading coefficient is 1, yes. Will you run into cases where the leading coefficient isn't 1 doing this? I don't think so. Emily. So the two numbers that would multiply to give you 25 over 4 and add to give you 5 are 5 over 2 and 5 over 2. Which is, that's all we're doing. And we don't have to think hard about the factoring because we made sure that the polynomial we created was a perfect square, so we knew exactly how it was going to factor. It has to factor that way because we made it factor that like that by adding that extra constant term in at the end. So we made sure it factored that way, so we didn't have to think about it too hard. Does that feel okay? Cool. These are all good questions, and they're all nice questions because it's like, oh, and it's always going to be that way? Yeah, okay, I'm good with just like hand wave at that thing then, right? But it's good to like really see it. You know what I mean? To really see it. All right, so we've gone from polar to rectangular, right? The worst case here is where we're going to run into these circles. That's the worst sort of situation I'm going to force you into. Okay? What if we want to go the other direction, though? What if we want to go from a polar function, from a rectangular function to a polar function? So let's start with something simple, like y equals 4. Remind me again, what is y?
R sine theta.
Yep. And then polar functions start with r equals. That's the independent variable. So divide both sides by sine theta. Right? And that is the same thing as yeah.
Wouldn't you just want to keep it in sine theta? Like, what does it really make a difference to actually change it to cosecant?
No. We can use an identity, so I figured I'd, most people like multiplication better than division.
Yeah.
But it didn't really make much difference to this guy. All right. You ready for some, what about this, though? Ruh-roh, Raggy. Yeah, that's exactly what I'd want to do first. There's a lot of foiling. What don't I want to say here? Don't do that. Mr. Kulik gets very sad. His life's sad enough without you guys making him sadder. Okay? Please, please, please don't distribute those exponents. I was grading homework quizzes last week, or over the weekend. So many distributed negatives. So many. Or distributed exponents. So many. Mr. Kulik was very sad. Okay? Everybody's okay here? Oh yeah, 12 on. Cool. Yep. Typo. All right. Now what do you see?
Subtract 36 and the 9 and 0.
Sure. Let's do that. Okay, what else? There's 3 other things here.
You could change it to change x squared and y squared into r probably.
Absolutely, yeah. Ooh, I forgot the plus sign here, huh? X squared plus y squared is r squared, excuse me. Okay. What else do you see? What's x? Yeah. R cosine theta. And what's y? R sine theta. Okay. Now what should I do? Well, I would add the 6r cosine theta and subtract the 12r sine theta from both sides, because you know you want the thetas on the other side of your equation, right? Because those are like the dependent variable. Now what? You're almost there. We need to have it r equals instead of r squared.
You could take out the r from the cosine theta, sine theta, and then just divide it out.
Okay, so divide both sides by r.
But you can't really do that yet because you have a subtraction sign. But can't you like?
You can distribute division, right? If you divide both sides, still the same thing. Now, I'm dividing by a variable. Can I do that?
It's not equal to 0.
If it's not equal to 0, great. What is r?
0.
Why?
That's a really good question. You can't prove that it's not 0.
Sure you can.
Can you just say it's like r not equal to 0?
Isn't r the radius of this circle?
Oh yeah.
Is that 0? No, man, because it's a circle, right? Can't have a circle with radius 0, right? Circle exists.
So that's true.
So you're good, right? No big deal. You don't have to think that hard about it. Like medium hard, not overtime hard. Feel okay? That wasn't so bad still, right? A little bit of tricky rearranging, but we're just using those same rearranging formulas that we used in the polar points, the rectangular points, right? Okay. Last section. Okay. So let's talk about graphs of polar functions. So the first thing we want to talk about is things like maximums or minimums and domains and ranges, and how do we deal with this with when we now have these polar functions? Okay. So what if I want the maximum or minimum for this function here? Yeah, you don't even need to graph it. So what's the range of values that cosine theta can have? What's the smallest value cosine theta can be? This is something we've done in class. -1 to +1. Very good. So that's the range for cosine theta, right? Those are the values that cosine theta can take, is things between -1 to +1. So the smallest value that r can take is going to be when cosine is equal to -1. And the biggest value r can take is when cosine theta is equal to +1. Everybody okay with that? So what's the range for r have to be then? 2 to 4. Let's just take a look at the picture and see if our picture supports that. What do you guys say? Yeah, why not, right? Sure looks like it. Right? We go from 2 to 4 on the r-axis. Does that feel good? It's my range, I guess we should say, for r. What do you guys think? That's not bad, right? What if we did the same thing for r equals 4 minus 3 sine theta? Yep. So the minimum is going to happen at when sine is +1, and the maximum will happen when sine is at -1. Why is it opposite like that? Because there's a negative sign in front of the sine, right? Since it's negative sign is actually biggest when it outputs -1, because negative of a negative is positive. You get the idea. What do you guys think? Not bad, right? Fairly straightforward, pretty numeric. Just relying on some previous knowledge that we had about sines and cosines. Let's talk now some symmetry. Do you guys remember the 3 types of symmetry? So there's symmetric about the x-axis. There's symmetry about the y-axis. And then do you remember the other one? we'll call it alpha degree point symmetry with respect to 0, 0. So it's rotational about the origin. So to determine if something has x-axis symmetry, we're going to do that. For y-axis, we do both of them. And then for our alpha point, we're going to add that to theta. Okay. So let's say we want to prove that r equals 5 sine 3 theta has y-axis symmetry and 120 degree point symmetry. We're going to do each of those two symmetries separately as their own separate proof. Okay. So we're going to rewrite our function, except we're going to replace our r's with negative r's and our thetas with negative thetas, and then see if we can simplify this down to be the same thing as the original. Okay. So I noticed that 3 times negative theta is just negative 3 theta. Everybody agree with that? So far, so good? I notice now an identity that I can use. Does anybody notice the identity? Maddie?
The sine of negative, the theta equals negative sine theta.
Yeah, the odd even identity that says sine of negative theta is equal to negative sine theta. And then if we divide both sides by negative 1, oops, forgot my 3. I'm done. Okay, so for the 120 point symmetry, we're going to replace r with r, so no change there. But we're going to replace theta with 120 degrees. Or alpha, I'm sorry, theta plus 120 degrees. So far, so good. Okay, I'm going to distribute the 3 inside my parentheses. Then I notice that I have a sine of a sum. Do you guys remember the identity for the sum of angles? The sine of a sum? No? Oops. That's a tougher one. So that was the identity there that I used. I just wrote out for you guys. We did that stuff in chapter 6. Cosine of 360 on the unit circle, I can look that up. What's cosine 360? 1. Awesome. And what's sine 360? 0. So this just turns into, oops, that's a 3 theta there. Just turns into 5 sine 3 theta. Oh, right on, Mr. K. Dunzos. Woo! Pretty cool. Let's look at the graph of this bad mama jamma here, just so we can observe this beautiful symmetry. Okay, 5 sine 3 theta, graph-a-roo. Whoa, look at that cool looking flower. Or airplane propeller? I don't know. This is actually a whole class, or represents a whole class of polar functions called rose curves. And let's talk a little bit about what those might look like. So those are of the form a cosine n theta or a sine n theta, where n is an integer that's greater than 1. The domain for theta is just going to always be all real numbers. Why'd I write it that way, dummy? Let's write it as a interval like we've been doing all class. Don't be a pooper scooper, Mr. Kulik. Okay. I wouldn't want to be a pooper scooper. There's our domain and range. The number of petals is going to be the same as the value for n. So if n is even, then our curve's going to have x and y axis symmetry along with alpha point symmetry. If n is odd, like we saw before, and we are dealing with a cosine function, actually we did a sine function as our example. So here for cosine we have x and alpha point symmetry. And if it's a sine one, that was the example we just looked at. There we have y-axis as well as alpha point. Oh my goodness. Okay, so let's say that we asked you to analyze r is equal to negative cosine 5 theta. Well, here my a is negative 6, and my n is 5, and my alpha would be 360 divided by 5, which is, what is that? Something or another. 72. Okay. So what I have is a rose curve. The domain is always all real numbers for a rose curve. The range is negative the absolute value of a to absolute value a. The maximum value for this is, well, that's silly, that's 6, and the minimum is negative 6. The number of petals on my rose graph is going to be n, so that's 5. And my symmetry, since we're odd and a cosine function, my symmetry is going to be x-axis and then 72-point symmetries. So if I look at that picture here right quick, we have negative 6 cosine 5 theta. There's my pretty flower there. The 72-point symmetry means that if I rotate this thing 72 degrees, like this petal would move to that petal's location. They all just kind of, turn, but they're in this, it's the same picture still. You know what I mean? You can see it, right? Okay. So we have rose curves. That's a whole class of function. There's another type called limazan. And this will be the last thing we talk about here. So this word here is pronounced limazan. It's somebody's last name. It's one of those C's with the tails on it. Foreign language people, what is that letter called? You have the C with the tail on it. Does anybody know? I don't remember what that's called. It has a name for it, though. Okay, deep sedilla. Sure. I don't know. All right. So the Limousin curves So let's talk about those guys. They are of the form a plus or minus b cosine theta or a plus or minus b sine theta. The domain, just like for the rose curves, is all real numbers. The range is going to be a minus b to a plus b. The max value then is going to be a plus b, and the min would be a minus b. Now there's three types of these guys, depending on, four types, excuse me, the relationship of a over b. So if that a divided by b is less than 1, it's an inner loop. If it's equal to exactly 1, it's called a cardioid, because it kind of looks like a heart. Cardio. If that is between 1 and 2, we call it dimpled. Has like a little indent in it, which is tough to tell the difference between that one and the cardioid one, to be honest with you. And then if it's bigger than 2 or bigger, I should say, it's convex. And there's like no dent in it at all. And the symmetries is really easy. The cosine ones have x-axis symmetry, and the sine ones have, not surprisingly, y-axis symmetry. So let's just do a couple of examples to show you guys these pictures of the inner loop cardioid dimpled and convex real quick. So let's say, oops, oh my goodness, what did I just do? Okay. I want you over here. All right, let's see. Over b. Okay, so that's 1 over 2. That's less than 1. So this should be an inner loop. And just for the sake of doing this, I'm going to turn off my axes so it's a little bit easier to see what's going on. So that's an inner loop. See how there's like a little loop inside of the big loop? Okay. I'll change this to 1 and 1. So that should be cardioid. So there it looks like a heart. Let's just change this to be a little bit smaller here. Or zoom this in a little bit so it's a little bit easier to see what's going on. So you could see like it kind of made a little bit of a heart there. It's hard to see. I think if maybe I do bigger ones, if I do that, we'll make it more hearty. There we go. See, there we go. That looks a little hearty, doesn't it? All right. Next one, I need it between 1 and 2. So let's make that one 3, and the other one will be 2. So this will be dimpled, There's my little dimple right there. Like a dimple like on a golf ball. It's like a little indent. Golfers, you know that? Like they're dimples. And the last one would be convex. So I just make that one 2 and this one 1. And it just kind of looks like a circle, right? It's all convex. Okay. Last example. We might ask you to like analyze something like 4 minus 3 sine theta. So my A is 4 and my B is 3. Notice that the A and B values are always positive, even though there's a sign in front of it. That sign's part of the formula, not part of the A and B value. So what we have is we have a Limousin curve. The domain is all real numbers. My maximum value is going to be A plus 3, or A plus B, so 7. And my minimum is going to be A minus B, so 1. So my range then is going to be from 1 to 7. If I take my A over B is 4/3, which is between 1 and 2. So that would tell me that this is the dimpled. And since it's the sine version, the symmetry is y-axis. And if we wanted to graph it, we could, right? And it's going to look like a dimply do nut. So it's that 4 minus 3. There's our little dimply do nut. Kind of looks like a button. And guess what we just did here today, folks? We did it! Yeah. So you guys should be able to do up through the finish, so 63 to 96. Hey,
No.
those, how about no? How about no? Get out of town. How about yes?